Hello everyone, this is Michael Abdelmalek. Today I'm going to present for you the paper entitled as A Markov Decision Process to Enhance Power System Operation Resilience During Hurricanes. In this paper, we are proposing a proactive generation redispatch for resilience enhancement. In this paper, it is required to determine the optimal actions to proactively redispatch generation at each time instant, considering the sequential reconfiguration of the system network due to failure of system components in order to minimize both operational and curtailment costs. This is important because of three main reasons. First, extreme weather events have severely impacted power systems and resulted in extended outages. Second, proactive and corrective strategies are given less attention over the restorative strategies. And third, resilience enhancement is a mathematically involved problem that requires high computational capabilities and a lot of model handling, complexity, and constraints. In this paper, we're going to propose a recursive Markov decision process to determine these optimal decisions based on the current system states as well as all the possible future states due to system component failures. Many system operational constraints are considered, such as power balance constraint and transmission line constraints. As a hurricane propagates through system network, various components will fail. As the propagation continues in time, various states will exist. A Markov state can be used to represent a specific network topology. In this paper, we use Markov decision process to determine the best action to be taken at each time instant given a specific state. These action once taken, a reward is given, which can be calculated through both the curtailment cost and the operational costs. As you can see in the figure here, a hurricane propagates through the IEEE 30 bus system, and the list of the failures at each time instant is presented in the table. The failure probability can be calculated through fragility curve models. The obtained result shows that the ramping behavior changes based on the failure scenario. In the figure at the bottom, you see the comparison between the generation profiles at each failure scenario and compared with the normal operation. As you can see from this figure, generator 1 and generator 2 usually are ramping down due to potential failures in the future. Also, generator 3 and 4 are ramping up to compensate for that reduction. Generator 6 comes to complete shutdown at turn T4 because of potential failure at T5. The load is curtailed at earlier time instant to avoid much curtailments in the future. Also, the total costs are reduced for various scenarios and conditions. In this paper, we tested three conditions of initial generation levels and compared them with the normal operation. You can see from the figure at the top that considering a very relaxed initial generation level will result in a total cost of almost the same as the normal operation cost. However, the operational cost might change. It will be higher at different levels and failure scenarios. In this paper, we have proposed a probabilistic proactive generation redispatch strategy to enhance the operational resilience of power grids during hurricanes. The proposed method minimizes both the load curtailments as well as the system operational cost under various system constraints such as power limits, transmission limits, generator status, and generator capacities and ramping behavior. The Markov decision process was utilized to model the spatiotemporal characteristic of hurricane propagation on components failure. The proposed idea showed the effectiveness of the algorithm to reduce or even eliminate the overall cost via proactive redispatching. In the future, the role of renewable energy resources on the generation redispatch will be studied.